plug in all of the pieces to our formula. So we add these two vectors together to get that, and then we'll plug into our actual function f. We've got two copies of the same expression. This guy's a 2. We'll rewrite it as a 2. And we'll do the algebra up top. When we multiply this in, we'll get a 2. That'll cancel this fellow over here. Now we can cancel the h's, right? Got a common factor of h. Right there. So I'd say this is a fine place to stop. I think that's nice. If if this is reminding you of awful memories of high school algebra or something, we can cancel. Those are equal. So we'll treat them as equal. Yep. Right, so let's see. Oh, yes, thank you. Right, so this guy, yes, this guy is here. Thank you. Yes, thank you for spotting that. That's huge. Yes, Micah?
Also, shouldn't it be plus h squared over 2?
Let's see. Plus h squared over 2?
Yeah.
Yes, perfect. Yes, nice. These are great contributions. Okay, so it gives us some slope. So what does this number represent? If we were, a little ant standing on the graph of this guy, and we walked in this direction, we would experience a particular slope, a particular rate of change, right? And notice that this rate of change is different, right? If we took the derivative in the direction x, we get 2. If we took the derivative in the direction y, we would also get 2. Right? If we take the partial derivative, we get 2x or 2y. But this is like bigger than both of those, right? This is a steeper direction to climb. Right? We'd be going up faster along that route. Yep.
Would the rate of change in an arbitrary direction only be the same as with x or y if the direction is the axis?
So for most functions, yes. But imagine that you just had a constant function that just always outputs like 7. Then the rate of change in all directions would be the same, right? So yeah, rate of change being equal to the rate of change of an axis doesn't mean that you'll live along the axis for sort of constant functions. Okay, so as you can see, the calculation with limits and stuff is always complicated. Now I want to give you a more sort of geometric approach to this that makes it a little bit nicer, a little bit kind of crisper. Right, okay. So right, in this setup, it seems kind of like a big algebraic nightmare. Now we'll give a geometric way of thinking about what's going on. So I'm going to draw this picture from the perspective of the xy plane. But remember that above that, there's a surface sitting, right? So we've got some function f of x, y, and we're just going to focus on the inputs, the x and y inputs. Okay, so if we've got a point AB, and we fix a direction v, then we can imagine a path that passes through the point AB in the direction V. Right? So we fix a point in space, and then we walk through that point in direction V. Okay? So there's a parameterized path that that? Yeah, let's not put coordinates. So there's a path that I'll call P of t. Passing through that point. Observe. That when we plug in 0, we get that output. And this path doesn't look tremendously different than the stuff that we've got here. Right? We've got our base point plus h times our direction vector. Here we've got our base point plus t times our direction vector. Similar things. Okay? So what we want to know is, how does our function change along this parameterized path? What is the rate of change as we walk along this path? So we can calculate this out. We can write out what this would be. And now this is a very lovely composition of functions. We've got a single variable input. Single variable splits into x and y. We put those into f, single variable output. Now we're back in the land of single variable functions, right? Single input, single output. So we can take derivatives. So we're going to get a rate of change for our function at that point in the direction v. Right? So this equality here is just based on the idea, so based on the notion that this path passes through AB in the direction B. And now we need to calculate this derivative. And what did you guys learn from Anastasia on Monday? Okay, what was the topic of Monday? Yes? Yeah, it's chain rule, right? And here we've got a chain situation. We've got function inside function. So let's look at how these functions depend upon the input t. So what do I want to say? Right, so I've got this kind of a chain of dependencies. When I change t, that changes x, that changes f. When I change t, that changes y, that changes f. Right, so what we get oops. So when we change t, we'll get some change in this guy. And some change in this guy. Okay, I should define these p1s and p2s. So we've got a change in this x coordinate that will affect the change in f according to the chain rule.